So I lied about saying we're gonna learn about equilibrium and stuff. We still got to go through two more things about vectors, and one of them will be the dot product. So by definition, the dot product is defined by this. So it's a little dot in between two vectors. And well, before we do that, let's define A and B as AXI plus B or AYJ plus AZK, and then B is defined similarly, so BXI plus BYJ plus BZK. So then the dot product is simply you multiply each like term with each other, so AX times BX, and then you add them, and then be AY BY plus AZ BZ. And what you want to know about this is a scalar quantity. So you're converting two vectors into a scalar quantity. So this is not a vector, this is just purely a number. But the actual true definition, which might be useful when finding angles, is that A dot B, is also equal to the magnitude of A times the magnitude of B times the cosine of the angle in between them. So let's say we have a vector pointing in this direction, vector A, and then we have a vector pointing in this direction, vector B. The angle in between them is theta, which can be useful if you want to find the angle between two vectors, two arbitrary vectors. And also, what's more important about this is the idea of projection. That is where most of this dot product is used. So, for instance, when you multiply A times B times cosine theta, you're basically taking the projection of this. You're finding the right angle of that and seeing what projects onto this vector. So when it becomes really useful is when one of these vectors are unit vectors, because you know the magnitude of a unit vector is equal to 1. So let's say A dot a unit vector, so it'll be the magnitude of A plus the magnitude of U times the cosine of theta. So what we're doing here, we're scaling the unit vector, or scaling A with the direction of the unit vector. So this would equal A, and this would equal 1, so it would be cosine theta. So if you want a representation of that, so the unit vector would be in this direction. So this will be U. And then A will be in that direction, which will be A. And then we project downward until we meet that. So then the A cosine theta, or A dot U, will be simply the length of this. And the reason why that's useful is because now we can project vectors in arbitrary directions instead of what we did before, which was in the I direction, the J direction, and or the K direction. Now we can arbitrarily project it into arbitrary directions in 3D space by using unit vectors instead of the traditional I, J, K vectors. So if you want to see a more clear example, we could project A onto onto the x-axis by doing A dot I, and they'll give you the AX component. Or if you want the Y component, you simply dot it with the J component, or J unit vector, and then similarly for the K unit vector, you get a Z. And if you want to see a more direct proof of that, we could define I and A and do the multiplication. So what we're going to do, we're going to define A A is defined like this. So we're going to define, let's say, I. I is the unit vector, so it'll be 1i plus 0j plus 0k. And we want to dot that with a. I'm going to rewrite a right here. So axi plus ayj plus azk. So as we defined earlier, a dot b is simply the multiplication of each corresponding component of the two vectors. So let's multiply. So a dot I will give you ax times 1 times I, oh, not times I, a times x, ax times 1 plus ay times 0 plus az times 0. So now you get ax. So now you get the projection of a onto the x-axis, which is just the magnitude of the x component of the vector. So this will become very useful in the future, and we'll be able to project various vectors into different directions and solve equilibrium problems.